let's do some iterated integrals just to get more practice at the process in general. Let's start off here. I want to evaluate this integral. So I'm going to do it first with y, then with x. So if I integrate this with respect to y, x is constant, so I get xy, but y is not constant, so I add 1 to the power, divide by the power, go from 0 to 2 dx. Then I sub in for y. And notice when y is 0, both of these terms vanish. So we're just going to plug in for 2. We get 2x plus, so y squared is 4. 4 divided by 2 is 2 dx. And then that's just x squared plus 2x from 0 to 1, which is 3. Okay, simple enough. When we have constant limits, usually not too bad on the iterated integral. This one has constant limits, but it's a little trickier. So what we want to do is we want to integrate with respect to y. But I'm going to do a trick here. I say it's a trick. I'm going to rewrite this as e to the x times e to the y dy dx. Now remember, that's how exponents work. Multiplying like this, you would add the exponents. So I'm going to split those apart. The reason why is because now this is a constant. And remember, the antiderivative of e to the y is just e to the y. Okay, so I get that, which e to the natural log 3, those are inverses, so that's a 3. And e to the 0 is 1, so I get 3 e to the x minus, that's 3 e to the x minus e to the x. So it's really just 2 e to the x dx, which antiderives to 2e to the x, which is 2e to the natural log 4 minus 2e to the 0. So again, those are inverses, so that's like 2 times 4 minus 2, 8 minus 2, which is 6. All right, so now we want to continue, and we're going to do this bad boy. This one's a little trickier, so I'm hoping we have enough board space. So I've got 4 over x squared plus y squared. Now I'm integrating with respect to x first. Now, if you go back to not just introductory calculus, but your second calculus course or whatever, you're going to recall that this requires something called trigonometric substitution. Now you might recognize it and be able to just snap it out, and you can go to an integral table. But trigonometric substitution is generally the way that this is done. So you take a look and you say, okay, well, if I construct a triangle, x, put x here, y, for some angle theta, right? You construct a triangle where the sides satisfy, some sort of Pythagorean identity. And then you try to work through what you might guess. Now, if you've had some practice, you remember which one to guess. But if you don't, you may have to play with it a little bit. So x over y is actually tangent of theta. And so then if I take the derivative of both sides, I get secant squared theta d theta is equal to 1 over y dx. Okay? What I also notice is if x over tangent theta is x over y, then x is y tangent of theta. And I'm not going to mess with these limits yet. So, using that substitution, I get y tan theta squared plus y squared. Instead of dx, I get, this is 1 over y dx. So, you need to write it like that. So then you end up with y secant squared theta d theta dy. So this is really y squared tangent squared theta. So if I pull out a y squared, I get that. Well, tangent squared theta plus 1, you may not remember, but that's an identity. Tangent squared theta plus 1 equals secant squared theta. And I'm going to go ahead and cancel one of the y's here. So now my secant squared thetas cancel. So I have 4 over y d theta dy. Well, taking the antiderivative here is fairly straightforward. 1 over 3, 4 over y theta from x equals 0 to x equals y dy. The problem is this is in terms of theta, but these are in terms of x. So I need to go all the way back here and say theta is tangent inverse or arctangent x over y. So now we have to plug in. We have to say, all right, well that's 4 over y arctan of 1, right, because it's y over y, minus 4 over y arctan of 0 dy. Okay, well, arctan of 1 is pi over 4, and arctan of 0 is 0. So this term actually cancels. So we end up with the integral from 1 to 3 of pi over y dy, which surprisingly is not too bad. Well, the 1 over y dy is just natural log of y, and then pi is the constant, so 1 to 3. Natural log of 3 is natural log 3. Natural log of 1 is 0. So we end up with pi natural log of 3. Sorry, I had to check my notes to make sure I did that right. So this is a long problem, but I wanted to point out the fact that you can still do it. It takes some time. You got to wrap your head around it. You may have to watch this a couple of times because I might have skipped too quickly over something. But the idea is that this can be done, and even advanced integral, or advanced integral techniques can be done using these things as constants. It all works the exact same. It just gets a little more complicated.